Okay. Right. So today is going to be pretty packed, and so is next Thursday. This problem set looks to be a bit long. Okay. Let me just set up one more thing I need to do. Okay. All right, I think I got everything in order. All right. Yeah, so for today, we're going to be going through more of this curve sketching process that we went through last time. Apparently, I anticipated that. Because like we have to talk about horizontal asymptotes, and I guess that you should know vertical asymptotes. Horizontal asymptotes are just when you take the limit of the function as x goes to plus or minus infinity. That's sort of the that's seeing like as you let x go to a very large number, what does the overall function do at the like ends of the function? And so yeah, that will indicate for you whether or not the function has a horizontal asymptote. Then we end up running through the whole curve sketch process for two problems, and we'll probably stop at this point. Right. So I think that for doing problems like 1 and 2, we'll probably want to show all of our algebraic work for it. But when it comes to actually doing those calculations for like the horizontal asymptote, like in 4 and 5, where we're given like very little space, we will just prioritize getting the answer. So we won't need to be all thorough with our algebra work. That's how I'm going to approach it. So to start off with, like, how would you just do one? Like, how would you just answer one? You don't actually need to show any algebraic calculation to answer this. No?
Would you just take 3/4 outside and then do limit as x approaches infinity of x to the 9 minus 9 power? And then simplify from there to get 3/4 eventually.
Yeah, I think, yeah, you're pretty much saying like to get rid of the lower order terms, and you're only looking at these two in front. Yeah, so you're absolutely right that the final answer that we expect to get is y is equal to 3/4. This would be the horizontal asymptote. Just by looking at this kind of function, we can tell right away. And that's because, well, first of all, because there's no square root. It's a very nice and easy function. All you have to do is look at the powers of the polynomials, and in this case, because they're both equal, then the answer, the horizontal asymptote, is just the ratio of the coefficients, the 3 and the 4. And this should kind of remind you of things that you probably learned from a previous like pre-calculus class. So yeah, you should also know about the cases when the numerator has a higher degree than the denominator, and also vice versa when the numerator has a lower degree than the denominator. Right? In one of those situations, you have a horizontal asymptote, which is y equals 0, and the other one, you don't have a horizontal asymptote. Right? So this is the non-rigorous way of doing it, and that's how we'll answer the ones that are like 4 and 5, where it just asks us to find the horizontal asymptote. We can do that without, I think, showing any real work. But for 1, because this is like the whole problem, let's actually show all of the detailed work. So for the detailed work, the idea is you're supposed to be using a limit as x goes to, and technically you're supposed to calculate 2 different limits, but because this problem doesn't have a square root, this is an easy case. And so what we can do is we can just calculate both directions simultaneously. It makes no difference. Yeah. Pretty much. Okay, there's one case in which it will make a difference, but that's in that case it doesn't even have a horizontal asymptote. So the whole thing goes to plus or minus infinity. Okay. Yeah. And then, well, right, you just copy things down. And then we do algebra to reduce what this thing ends up being. Right. So the algebra that we need to perform here is we want to divide by the as many x's as possible to actually get rid of these lower order terms. Once we have x in the denominator, we know that the limit of something with x in the denominator, if you let the limit go to x goes to infinity, then you're just gonna get 0 for that. So that'll get rid of a lot of the terms. And so what we will do is we divide top and bottom by x to the 9th. My cursor's being a bit funny, because the additional benefit for that is it makes this become 3, it makes this become 4. So we end up having these leading terms really show their significance. For minus 7 over x to the 5th plus 3 over x to the 8th. Right. And so, yeah, now when you actually take the limit of this expression, you can imagine the limit splitting over the fraction and then splitting over every single term in the numerator or every single term in the denominator. And all of the terms that have x in them, they're going to go to 0. And so we can then just conclude this is equal to 3 over 4. So this is how you would do it rigorously. And I'm pretty sure that Craig does it in his videos, in his slides. That this is the easy part. Right. 2 is a bit more tricky because of that square root. So there's the key thing that underpins this problem is thinking about this expression, square root of x squared. And the common thing that people will say is that this is equal to x, and that's only half of the story. This is equal to x so long as x is greater than or equal to 0. Otherwise, it's equal to minus x. Then I guess I should say that's for when x is negative, right? Because when x is a negative number, pick like -3. When you square it, you're going to get 9. When you take the square root, you're going to get 3. So you started at -3, you ended at +3. What happened is you sort of took an absolute value. You kind of you negated the thing. Like this right-hand side expression is the same thing as taking the absolute value, but usually we don't want to have an absolute value show up. Well, the key thing here is that the answer that we get out, or the simplification that we'll have, is going to depend on which limit we're talking about. So approaching minus infinity is going to give us a different answer than approaching positive infinity. And it's all because of this algebraic step. But otherwise, like, it's pretty similar, I guess. Yeah, all the steps are the same, except for this one little change that happens. So what we want to do, just like before, is we want to take a limit, and this time we have to spell out the difference between plus infinity and minus infinity. And well, so how do we get this thing to show up? Well, what we do is we'll factor an x squared from this the expression inside of the square root. So if I factor an x squared, I'm going to get a 4 plus 7 over x squared. Okay, divided by and I guess to preempt it, I'll divide out by x denominator as well. Okay, and one property about square roots or about exponents is that you can split it over a multiplication like this. So this is the same thing as square root of x squared times square root of 4 plus 7 over x squared. And that's where the simplification is going to happen. So it's going to look like I'm not doing anything in this step, but well, this application of the rule, square root of x squared, it becomes positive x because we're approaching x, we're approaching positive infinity. And so this square root of x squared expression is always the positive version. 7 over x squared like so. And then there's going to be the cancellation there. I'm just spelling out things a bit more. Oh, I meant to switch colors. Oh well. Right. And then I think here we can plug in. So I want to save a bit of space because I don't really have that much space. Let me just evaluate at this point. So this will just be square root of 4 over 5, which is going to be 2 over 5. Okay, so that is one of the horizontal asymptotes. If you approach x equals positive infinity, you get y equals 2 over 5. Then you basically have to do the same thing for the other side. Yeah, let me just copy paste. I think that'll be fine, hopefully. Okay, that's weird. It's because it's set to keep source formatting. Should really change that. How do I change that from here? Let's reset the default. I changed it once and then it screws it up all the rest of the time. That's great. Okay. Right. So the other sided limit, it is the same, except we're going to minus infinity, and this becomes minus x, right? So we would split the square root, and then we have square root of x squared, but because we're on the negative end, we end up using this branch where it equals minus x, and so we have this minus, and so that's a bit strange. Okay, and so this ends up being negative square root of 4 over 5, which gives you negative 2 over 5. Okay, so this problem actually has 2 horizontal asymptotes. Again, this is something you can kind of do without actually calculating, just as long as you're sort of able to like think forward and see all these steps. Like you would just like with number 1, with these lower order terms disappearing, you would expect like these lower order terms would also disappear, and you only care about like the square root of 4x squared divided by 5x, and then you can kind of estimate. So yeah, let's do this in a kind of approximate case. So you kind of estimate that this is going to behave like square root of 4x squared over 5x, and that is just going to be plus or minus 2 over 5. When you take the square root this time around, you just have to like put the plus or minus in front to be cautious about this kind of splitting that happens. Okay. Any questions so far? I need to charge my laptop. Okay. What's next? 3. So first thing is to write a formula. So that's obviously the most important step. Otherwise, everything else is wrong. So we're going to write a formula for concentration. Okay. We have brine water at 50 grams per liter, salt pumped into a tank at a rate of 3 liters per minute. How did I answer this? Okay, so there's a bit of a unit conversion. The rate that is being pumped in is 3 liters per minute, and the brine water is actually 50 grams per liter. So, what am I trying to say? Yeah, so 50 grams per liter times 3 liters per minute is going to end up giving you 150 grams per minute. So this is how much brine water is flowing in 1 minute. And then Right. Okay. Yeah. So the idea for concentration is it's amount divided by volume. So this is the amount, and then you have to then divide it by the volume. So amount here is 150. T, how much time elapses, divided by, and then volume is going to be 1,000 liters plus the 3T liters from the flowing in. And so then the full units is going to be in terms of grams per liter, right? So if you just think about it, this formula is going to make sense. And then for part B, we have to just take the limit as t goes to infinity of this expression. And well, we can do this without doing all the algebra, I think. I mean, if you want to do the algebra, you can. But yeah, this will just be take the ratio of the leading coefficients. So that's just going to end up being 50 liters per, or grams per liter, 50 grams per liter. Okay. And for interpreting, well, this is saying that the concentration, well, you can just phrase the whole thing back into words, right? As if you let this process go on long enough, the concentration is going to approach 50 grams per liter. There's like kind of a tendency to want to use like the word equilibrium for this problem. So I guess what I wrote down here is the tank will approach an equilibrium of 50 grams per liter. I don't know if it's actually technically an equilibrium, but it's gonna tend towards that value. Just let the process go on long enough and it'll be indistinguishable at some point. So yeah, hopefully that makes sense. And 4 and 5, we run through the whole curve sketch process. So again, the curve sketch process is just a way of gathering all the data that we can about a function, and usually it'll be a rational function. In both of these problems, it is a rational function. Domain, intercepts, horizontal and vertical asymptotes, increasing and decreasing, concave up, concave down, inflection points, local min, local max, right? Get as much data as we can about the function. Also, we can then graph it. Yeah. All right, so let's go ahead and do this. The domain, well, the easy way to write this is that x is not equal to 2 or -2. If you want to, you could write this in interval notation, like all the real numbers excluding these two things. It's just a union of 3 intervals. The y-intercepts, so what you have to remember is that y-intercepts are where x equals 0, and x-intercepts are where y equals 0. It's kind of the reverse. Yeah, it kind of reverses the statement. The reason is because intercepts are the things that intersect that axis. So y-intercepts intersect the y-axis, hence x has to equal 0. So if you think about it like that, then you know for the y-intercepts, we're plugging in x is equal to 0, and we're getting some number out, which is 9/4. Whereas x-intercepts, that's when y is equal to 0, and for that we have to imagine that this left-hand side is equal to 0, and we solve. And for that, we're going to get plus or minus 2 or 3, plus or minus 3. I'll just write 2. Okay. Do you guys know what even and odd mean? Does anyone not know what it means? I think I remember people tending to not remember that, so I'll just quickly recap. So an even function is a function that satisfies f of minus x is equal to f of x, whereas an odd function is something that satisfies f of minus x is equal to minus f of x. So what happens is like the way you test a function, just if you're just given a function, like by definition, what you do is you plug in minus x into that function and you see, does it equal the original function itself, or does it equal the negative of itself? And it can do one of those two things. It could also do neither. It could just be something completely different. But if it does satisfy one of those, it's the corresponding name is even or odd. And the typical examples that you have for that are things like x to the x squared, x cubed, x is some even power, x is some odd power. Also, you have cosine and you have sine. So cosine and sine, cosine is even, sine is odd. Usually you see this visually in terms of like reflection symmetry versus rotational symmetry. But yeah, in terms of just being given the definition of the function and being asked to figure out is it even or odd, what you do is you plug in minus x and you see what holds. And so for this, what you see is that the negative x is going to get squared immediately. So that's going to make the negative disappear. And so you end up back where you started. So this function is actually even. Okay. Vertical asymptotes, well, the vertical asymptotes occur when the denominator is equal to 0. That's just plus or minus 2. So we have x is equal to plus or minus 2. Horizontal asymptotes, we take the limit of this function as x goes to infinity, plus or minus. And, well, it's just going to be ratio of the leading coefficients. So it's going to be 1 over 1. You get y is equal to 1. Okay, now, unfortunately, we have to calculate two derivatives. It doesn't give us the derivatives. So for this problem, which actually this is the way that you're typically taught it. Like, yeah, when you're just told to like do a problem on this stuff, you end up needing to calculate these derivatives, and it's definitely a pain. But yeah, let's just do that. X squared minus 4 times derivative, so 2x minus x squared minus 9 times 2x over x squared minus 4 squared. Right. And we can simplify it, can't we? All right, so I'm just gonna look into this. So this x squared and this minus x squared should cancel each other. They're multiplied by 2x in common, so we just imagine distributing it. Those will cancel. We're left with a, how do I do this? 2x times 9 minus 4 over x squared minus 4 quantity squared. So this is a 10x over x squared minus 4 quantity squared. And that's all you can do to this. Right. Okay. And so now we can answer G, which in order to do that, it's best to just create a sign chart for this function. So let's go ahead and draw a sign chart. So the points that matter are, so normally what you do is you set this equal to 0 and solve, and you also see when is this f h prime, when is this h prime undefined. So when is the denominator equal 0, when is the numerator equal to 0? Numerator equals 0 at 0, denominator equals 0 at minus 2 and 2. And so now we need to do a sign chart, and noticing that all of these values are going to, it's going to alternate over every single one of these values because the powers that they're raised to, actually, no, it doesn't, not over every single one, sorry. This guy factorizes like x minus 2, x plus 2, but then because of the square, of, you know that around 2 and around minus 2, the sign is the same. Actually, it doesn't alternate. That was wrong. So plus, plus, minus, minus is the sign chart for this. And if you didn't follow that, you can pick numbers and plug things in and you'll get the same thing. Intervals increasing, decreasing, well, I just read it off. So 0 to 2, union 2 to infinity, decreasing minus infinity to minus 2, union minus 2 to 0. Local max, there aren't any, right? Local min, it's at 0. So it's going to be 0, comma and then I plug in. So it wants me to write it in coordinate form. So I figure out what this actual coordinate is. It's going to be 9/4. Right. I'm going to pause here. Any questions so far?
Or does that say none?
None.
Okay, thank you.
That's it. Okay. Right. So I saw a thumbs up. If there aren't any other questions, then we're going to do the second half of this one problem. This is just one problem. Okay. Yeah. So now we need to take another derivative, and I think it's about the same difficulty. Right. So again, quotient rule. X squared minus 4 quantity squared times 10 minus, make that a minus 10x times 2x squared minus 4 times a 2x all over x squared minus 4, and then we square the squared, so 4th power. And notice that we can cancel a little bit. This every term in here has a x squared minus 4, so I can get rid of one copy here, one copy there, and one copy there. Let's see, how much does that simplify? 2, I have 40x squared, negative 40x squared, wait, no, negative 40? Yeah, negative 40, and then plus 10. So I think I can just calculate what this ends up being. Negative 40x squared plus 10x squared, so negative 30x squared minus 40. Yeah, okay, great. And then I can factor that just a little so that I can reason about this better. So this is a negative 10 in front, x squared minus 4 over, wait, really? Plus 4. Yeah, plus 4. X squared plus 4, 3, there's a 3. Yeah, 3x squared plus 4 over x squared minus 4 cubed. That should be a cube. Okay. Yeah, so that matches with what I previously did. So that's right. Okay. Yeah, I'm making stupid mistakes right now. Okay. And then in order to answer the next part, part J with the concave up and down, well, another sign chart would be helpful just so we can visually see like what's going on. And you'll notice like we still have the -2 and +2 from before. Those are vertical asymptotes, so it kind of makes sense that they stay around. And notice that the numerator is never going to equal 0. So 3x squared plus 4 is always positive. It's always greater than 4, greater than or equal to 4. And the whole fraction is actually has a negative 10 in front. So if I plug in the rightmost region, I'm going to have well, the stuff in parentheses is all positive, but the negative 10 makes it negative. So I have a negative there. And then, well, what happens when we jump over 2? When we jump over -2? Well, we look at this guy in the denominator, because that's where the 2 and -2 come into play. Like you factor the thing and you have x minus 2 quantity cubed, x plus 2 quantity cubed. Well, the fact that they're cubed, that's an odd number, means that it is actually going to alternate. So we have an alternating thing happen. It's going to flip in sign when we jump over 2 and when we jump over -2. So that is our sign chart. And again, if you aren't comfortable with the process, you could plug in numbers. It'll be a bit more tedious, but yeah, you'll see that that's correct. And then we can answer concave up and down. So concave up is positive part, that's -2 to 2, and concave down is the negative part, negative infinity to -2, union 2 to infinity. And lastly, inflection points. So for this is one of the more subtle things. So you would want to say that the inflection points are at -2 and 2 because the concavity changes there. But then when you kind of look back on your function, you realize that -2 and 2 are vertical asymptotes, which means you can't actually plug in -2 and 2 into the function. And the subtle thing is that an inflection point is supposed to be a point on the curve. It's supposed to be actually a location that we can like point to on the curve that like the where the curvature changes, the concavity changes. Since it instead is happening at an asymptote, we don't consider those to be inflection points. So for K, it's none as well. I'm hearing something. Question?
Oh no, my bad.
Okay. All right. So with all of that, we now have all the data, and we can go ahead and graph this thing. So it would make sense to start with like the points and the asymptotes. So asymptotes at -2 and 2. Let's just draw those. And this thing has a horizontal asymptote of y equals 1, I remember. I'm just trying to be careful about this. And let's see, what else do we have? Intercepts at 3, -3, and 9/4. Okay, so 3 and -3, 0. So that's a point here and a point here. And 0, 9/3, 2 1/4, right? So that's like around here. Yeah, 2 1/4. Okay. Next we make sure all the regions are satisfied. So I think usually, yeah, usually what I'll do is, well, if you had this printed, you'd be able to more easily like just see, but I'm gonna copy it over to yeah. So we have it in front of us. So let's see. Over on this end, it's supposed to be increasing and negative concavity, so we can pretty much shape it like so. We also need to make sure that it matches up with the asymptote lines. From -2 to 2, it's decreasing and then increasing, and it's concave up. So that kind of makes you think it looks like this, right? I tend to put arrows on the ends. And then to the left of -2, it's decreasing and concave down. So it'll look like that. There we go. And you could have perhaps used the property about it being even to like, I don't know, do it on one half and then do it on the other half. I tend not to use even or odd. But yeah, some people might prefer to use that. Okay, so we end up with this graph. Any questions on this problem? Okay. No questions? Then let's do 5, and we'll see if, I don't know, maybe I can do a little bit more. I'm not sure. Depends on how troublesome the other ones are. Okay, domain. Right, so you look at this guy and you realize that the denominator is never equal to 0, right? It's always positive. So that means that the domain of this is everything. We should just put -infinity to infinity. Y-intercepts, so again, that's when x is equal to 0. If I plug 0 in, I'm going to get 0/1, so I get 0/0. X-intercepts, that's when y is equal to 0. If I set this equal to 0 here, I solve, I'll get that the x value is equal to 0. So we just have this point at the origin. It's a bit simpler, seems like. Okay, is it even or odd in this case? So if you imagine replacing x by -x in the function, right? This is going to square the negative away, but this is going to make the negative pop out, and the negative will pop out in front of the 4, and then it'll pop out in front of the whole function. So we end up with negative g of x when you do the algebra. So this is actually odd. For vertical asymptotes, well, again, denominator cannot equal 0, so there are none. Horizontal asymptotes, when you take the limit as x goes to plus or minus infinity, you end up, well, you notice that like the denominator is higher in degree than the numerator, which means that the denominator is going to dominate, and your horizontal asymptote is just y is equal to 0. Yeah, so that's all of that. And next we have to do the derivative. So x squared plus 1 times 4 minus 4x times 2x over x squared plus 1 quantity squared, I think. Minus 8x squared plus 4x squared. So that's a minus 4x squared plus 4 over x squared plus 1. Make that look like a 1. Quantity squared. And then I can pull in minus 4 out of that. I'll get x squared minus 1. Yeah, right. And then we can do a sign chart for this. So we have plus and minus 1. Those are the only things that we only critical numbers. Right? It's never undefined, and when you set equal to 0 and solve, you just get plus or minus 1. Okay, and now noticing that you have a negative 4 in front and this squared over here, that means that over here we have that this is negative. And then the plus or minus 1, the contributions are coming from this, the factorization of this x squared minus 1. So the exponent is just 1, so it's going to alternate. So this is going to be plus, and it's going to be minus. And now increasing and decreasing, we can just answer. Next, we've got local mins and maxes. So, right, yeah, in this case, it does have for both, I believe. So a max is going to happen from going from a plus to a minus. So there's one at 1 comma, and I need to plug in. So if I plug in 1, 4 over 2, so I get 2. Okay. Local min, if I plug in minus 1, I get minus 4 over 2, minus 2. Right. Any questions so far? No, everyone's okay. All right. Oh, now we have to do another derivative. I'll be looking at this one, I think, since I can take a derivative of that more easily. Right. So x squared plus 1 quantity squared times, I don't like this, times a negative 8x minus negative 4x squared plus 4 times a 2x squared plus 1 times a 2x. Yeah, over x squared plus 1 to the 4th power. Okay, well, like before, there's a cancellation, so I can get rid of this 1 copy from everywhere. That's helpful. Just a bit. Let's see. But I think I have x cubes, don't I? I have x cubes. Great. So minus 8x cubed and 2, 4 plus 16 x cubed. Yeah. Minus 8 plus 16. So I have an 8x cubed and then minus 8x minus 16x for 4, 16 minus 8 minus, so minus 24x. Let me just check. Yeah. Minus 24x over x squared plus 1. Okay. I wasn't paying attention to one minor detail. That's fine. X squared plus 1 all cubed. Okay, great. And then we factorize that a little bit just to make it look nice. X squared minus 3 over x squared plus 1 cubed. Yeah, I think that's right. Yeah. Okay. And so notice that now for this, when we set this equal to 0 and we solve, we get 3 points, 3 locations for our g double prime. We have 0, we have √3, and we have minus √3. So it's a bit annoying that there's a minus √3 showing up, but that's the right answer. And it's going to alternate on every single one of these, and it's positive to start with, so plus minus plus minus. Notice that the denominator doesn't contribute anything; it's always positive. Okay, and now concave up and concave down. We can just read that off. Minus √3 to 0, union √3 to infinity. Concave down is minus infinity to minus √3, union 0 to √3. Make that look a little bit nicer. And inflection points, well, it looks like there are 3 of them. It wants us to write them in coordinate form. So, right, once we start looking at them, we actually need to plug them in. That's interesting. Well, so let's see what happens if we plug in. So g of that is 4 times. So let's see what happens if we plug in g of, let's just start with √3. So we get 4 times √3 over 3 plus 1. That's what the expression says. We square the value plugging in and we add 1 to it. So we end up canceling that 4. Where's my cursor? We cancel that 4, so we end up with that. If we plug in 0, well, that's just going to be, 4 times 0 over 1. So 0, that's good. And then at negative √3, we get negative 4 √3. The squaring is going to get rid of the negative, so we still end up with 3 plus 1. And so we end up with negative √3. And that gives us our 3 points. So we have √3, comma, √3. We have 0, comma, 0. And we have negative √3, negative √3. And now to graph these things, just you should be aware that √3 is approximately 1.7. And we have a bunch of points to put it down. Do we have vertical asymptotes? No vertical asymptotes, a horizontal asymptote. Okay, so I'll just maybe put some dash lines to remind myself. And then at 1.7, 1.7 is around here. Negative 1.7, 1.7 is around here. And then what are we doing for the increase and decreasing? Again, let's copy it just to make it a bit easier for us. Can I do that? It still doesn't want to behave for me. Reset the default. Okay. Right. So after 1, it's decreasing, but there's a concavity change. Do I have maxes? I do have maxes somewhere. Yeah, 1, 2, -1, -2. Okay, so I have 2 more points that I can put. 1, comma 2 is up here. That's a max. -1, -2 is a local min. So we know that it's curving like so. And then Well, it's decreasing, but there's a concavity change at this point where it goes from being concave down to concave up. So that you've got to carefully sketch out and just make it, I guess, look like that. And then it's increasing but concave down, so that should look something like this. And then, well, in this case, probably just because this is an odd function, you kind of know what the rest of this should look like. But yeah, increasing concave up, something like, can't draw straight. Wait, is this supposed to be down? Yeah, this is supposed to be down. Why does that look not down? Down followed by concave up. So it looks something like this. It's very hard to use this little tablet thing. Okay. Yeah, so that's what that's supposed to look like. Any questions on this problem? Or any of those problems? Okay. Well, we're sort of at time, but I think that realistically, for the next for Thursday, I'm not going to be able to do the problems in full detail. There's a lot of algebra involved when it comes to like simplifying and solving. So probably what I'll end up doing is I'll skip a few steps, but they should be steps that like they're just algebra, so you should be able to fill them in when you're actually writing up your solutions for your homework. But yeah, so next week, or not next week, next time we're going to be doing things involving optimization, and it's there's something called the closed interval method. I'll try to refresh on that, but you can find what the corresponding information in the slides and the lecture. Closed interval method, and there's like a little caveat to what if you don't have a closed interval? What if your interval, the natural interval that you come up with, what if that's 0 to infinity, which for some of these problems it is. So we'll see how we deal with that next time.